We've done the Dirac equation in two ways. We've done it fundamentally from the parameter group, and we've done it from conventional theory, working backwards. Now let's see what we can do with it. So we're going to look at interacting fermions, the next level of complexity. And what we're going to do is three things. We're going to start with the non-local structures. Remember that last time we had that the inside the bracket is local, outside the bracket is non-local. And the things that we mean by non-local are things like superposition states, combination states, that kind of thing. Not what's inside the bracket. So we'll see the non-local structures that emerge naturally from the formalism. And then we'll see how these non-local structures have local consequences. So in other words, the non-local structure can change something inside the bracket and create, for example, a potential. So the potential will alter what's inside the bracket. Local potential to add to the energy momentum operators. And then what we will see is that if we change inside the bracket in a certain way, we will get the same effect as we got from the non-local structures outside. So that's and then we'll finally show that if we define the nilpotent operators we do now, we will have just three nilpotent solutions, only three, for any such potential. So we need to talk about bosons. We've talked entirely about fermions. Now we need to talk about bosons. And these are different from fermions in having scalar wave functions. So they don't have any quaternion structure. They have a scalar structure. And they're not Pauli exclusive. And we've not really properly explained why bosons are like that, why fermions are like they are. I've mentioned this already. The nilpotent force spin is composed of the lead term and then three other terms. We now know from the last lecture where the three other terms come from. They come from the C, P and T altered states, transformed states. So if we do those three transformations, we will get the three other terms. So in other words, they're the kind of possible states in which we could transform the lead term without changing its energy or momentum magnitude. And I will also show that we can see them as vacuum reflections of the actual particle state. Pauli exclusion, of course, says that we can't combine a fermion with itself because we'll get zero immediately. But what we can do is combine a fermion with one or other of those vacuum reflections, and we will then get a boson. If the reflection exists or materials of the real state, then the combined state can be one of the three classes of bosons. We've got three vacuum reflections, three bosons. So let's see how we do it. This is the first type of boson. This is the type that becomes the carrier of gauge forces, the strong electric and weak forces are bosons of this nature. This is a spin 1 boson. Now imagine that's a row, so you've got four terms in a row. This is a column, four terms in a column, and this is the scalar product of them. And so that term multiplies by that one, by that one, and that one by that one, and we add them. And that would be the scalar product. And I say this is a boson because you've got fermion here, positive at the top, and anti-fermion here, negative at the top. And you've got a spin 1 because you've got spins going the same way, plus and plus. So that's spin 1. You can see what that's what an anti-fermion of this kind would look like. So that's a spin 1 boson. Now, one thing that's interesting is that we can make this spin 1 boson massless. So that's with mass, and we just imagine making the mass 0, and we can make it massless. We still get a scalar value. This will still be a non-zero scalar when we multiply it all out. And we do have such spin 1 massless bosons. We have gluons, we have photons. So it ought to be possible, and we can do it. Now let's look at what might be a spin 0 boson. So we reverse the spin on that one. We could have reversed the spin on this one instead. It doesn't make any difference which has got the reverse spin, but one of them has to have. And here, again, you'll see that if you multiply all this out, if you actually bother doing the multiplication, you'll see that this works out to be a non-zero scalar. Now, interestingly, in this case, imagine that we reduce the mass to 0. In this case, we can't do it because if there's no mass, then E squared equals P squared, and this becomes minus E squared, or plus E squared minus P squared, or minus E squared plus P squared. It certainly becomes a zero value. So we cannot do it with a spin zero boson structured like this. So the implication is that a spin zero boson, for example, a hypothetical Goldstone boson, cannot exist. And Higgs is a spin zero, and a particle like the Higgs must have a mass according to this way of thinking. We will talk more about this, but the mass will work out as a measure of the degree of right-handedness of the fermion and left-handedness of the antifermion. So here, well, we'll leave that for now. We'll go back to that later. A massless spin zero boson must be made up of a left-handed fermion, which the weak interaction allows left-handed fermions. It doesn't allow right-handed. We briefly touched on that in the last lecture. A left-handed fermion is weak prohibited. So that's, say, what a left-handed fermion might look like. Let's imagine that. Or it could be a right-handed fermion, antifermion. I'm sorry, a right-handed fermion is weak prohibited, but a right-handed antifermion is weak allowed. So it could be like that. So if we want to overcome this prohibition, we must generate mass. And we've got a classic example of that in the Higgs, which we mentioned. Now, interestingly, the mass of the Higgs is about 126. This is absolute total speculation. But not that long, about a year before the Higgs mass was found, I thought it might be about 123, on the basis that you're splitting the vacuum at 246. We know the vacuum's 246 expectation value. You're splitting the vacuum up into a weak allowed bit and a weak prohibited bit. So the two possible ways of doing it might be how the vacuum is constructed. Well, it's not quite 246, it's more like 252. Interestingly, 252 is the sum of the masses of the weak bosons. I'm still investigating what that may mean.
That's pure speculation.
It's pure speculation. We don't know yet, we'll see. But I'm just saying it's worth looking at. That might be the reason. But I don't claim any big idea on that. This is the third type of boson. A third type of boson can be created by putting together two fermion states. Now, notice this is no longer antifermion, it's fermion. But this is spin zero because the spins are the opposite way. Again, this is a pure scalar, and this is what we would expect for something like Cooper pairs. Two fermion. In helium-4, Bose-Einstein condensates, we'd expect it for that. And then there's several other effects where you get the effect of a boson being created this way. This is a electron and nucleus connection. This is electron and solenoid, magnetic solenoid. The quantum Hall effect is electron and flux line. And these are non-zero Berry phase. So they're kind of pseudo-boson, or even boson. You'd expect spin zero, but there is one of these that's spin one. And that sort of I found a bit puzzling at the time, but then I worked out what I thought was the probable reason. The one that's spin one is helium-3. Now helium-3 isn't like the others. All these others, the connection is direct. It's not two separate pieces. It's two separate pieces, but they act together. In the case of helium-3, they don't. They act oppositely, and they move around opposite each other. And I suspect it's something like a harmonic oscillator movement. Now, if you've got spins the same, but helicity is different, then you can get spin one. Because helicity is the spin in the direction of momentum. So I think that's how that works. In the case of this state, fermion-fermion, we can make a prediction which is being tested by experiment. And I'm told that this is being tested, or will be very shortly. There's an experiment going to go on to test this, specifically from my own prediction. This state requires massive components. So what we're interested in is one where we can start off with a massless component. What we need is something like a Berry phase structure as we had before, and I think the easiest one to observe will be the quantum Hall effect, where electron and flux line form the combination. Now, if we take something special like graphene, the conduction electrons have zero effective mass, and this type of Hamiltonian, so there's no mass in it. Vf is the Fermi velocity, that replaces the velocity of light in graphene. And so we can imagine if they are massless and therefore one-handed, because massless particles must be one-handed, as we saw from the last lecture. We had to do it quickly, but that's one of the things we did in it. Massless particles must be one-handed. So normally in graphene the electrons are one-handed. If we can make it if we can apply a magnetic field in such a way as the electron can form a pseudo-bosonic combination with a flux line, then we can effectively change the parity state of the electron, because we're doing a weak interaction. If we can change the parity state of the electron, in other words, introduce a bit of right-handedness into what is otherwise total left-handed, then we will give that massless state a little bit of mass. If it has a bit of mass, then its velocity will drop below the Fermi velocity. And the experiment I've proposed is that we look at something like the quantum Hall effect in graphene and see if we get reduction in the Fermi velocity at appropriate moments. So that experiment is going to go ahead. So that's a definite prediction, and there's no speculation or numerology, that's a definite physical prediction. Okay, bosons are not an independent thing of fermions. Bosons and fermions are part of the same sort of organised structure. If you could combine a fermion with its own vacuum, it would annihilate. Now we can't, because that vacuum is everything else. So it would have to be combined with everything else to do it. But we could imagine it combining with a component of vacuum, and that's effectively what we're doing. In those three possible bosonic states, we're combining a fermion with part of the vacuum, three different parts of the vacuum. So we can see this as a simultaneous realization of the two vector spaces. We make one, but at the expense of making the vacuum space only one component. And it's a bit like having only one direction of angular momentum. It's the same sort of idea. Now I want to talk a little bit about the weak interaction here. The spin-1 bosons are the gauge particles, the transmitters of all local interactions. But there's a particularly interesting way in which they occur in the weak interaction. In the weak interaction, fermions and antifermions are annihilated and bosons are created. Or bosons annihilated and fermions and antifermions are created. Or both happen at the same time. And we can recognize this as the creation and annihilation states of a harmonic oscillator. And that's why we get unit energy levels for bosons as opposed to half. And we can also think of it as the creation and annihilation of the weak source, what I call the weak charge. So bosons don't have any weak source. Fermions do, but bosons don't. All fermions do, no bosons do. So even the particles that are transmitters of that force, the weak bosons, the W's and Z's, don't have weak charges. They can have electric charges, but not weak ones. And so I'm saying bosons created at antifermion fermion vertices are the products of weak interactions. And this happens even in things like electron-positron collisions. In electron-positron collisions, to a large extent, we're interested in the electric force, the cancellation of the positive and negative electric charges. But there is also an amplitude for a weak interaction in the process. It's not totally separate. There is an aspect of the weak interaction in the process. And now I want to look at a different interaction, the strong interaction. I wanted to look at baryons. These are the only other significant particles that we can be interested in here. Fermions are created as singularities in a double space structure. Now what baryons do is complicate this by introducing an explicit three-dimensionality. There are three component objects: protons, neutrons, the like. They're an expression of the fact that singularities are incompatible with pure three-dimensional space. So we need a dual space to create a singularity, and therefore we need to express this three-dimensionality in some specific way. Now it would seem that the strong interaction, which only occurs between these things and the bosons which are exchanged in them, that the strong interaction begins in a combination state, which reflects that the fact that P, the P term, is in fact a vector. It's just not one term, it's three. So I'm saying the quarks in a baryon, in a proton or neutron or the like, are components of a vector. And you can no more separate them than you can separate the directions of space in that context. So let's do it mathematically, which we can. Let's suppose we do that. Then I think you'll know the answer to that is immediately zero. We can't do that, ever. We can't just put three of the same, of a specific reason for doing the two signs of P in there, which I'll mention in a moment. But you can't do three such things as that because they're nilpotent, they'll zero straight away. What we can do is do this. Let's make that one a px component, a py component, a pz. And of course the labels are arbitrary, but as long as we've got the equivalent information of that in the system. Now, what will happen, let's imagine that all the momentum is in this component at one moment. Then that one will zero and that one will zero. And if all the momentum's in that component, then that one will zero and that one will. And so we can imagine that there are a number of phases, if you like, in which the momentum is in one of these components or another, and that the total is some combination of those phases. Here we are. That's all in the x component, that's all in the y component, that's all in the z component. Now, if we do that, so there's no more information than that. If we have that information, then that will describe the entire system. If we multiply this out, if I multiply this out mathematically, what I will get is some scalar times that. So effectively that multiplied out will become just that. So if I multiply that out, again it will be a scalar times that. We can get rid of the scalar by normalizing it. So we just ignore the scalar, we will get that as a result of the multiplication. Interestingly, this one is different. If I multiply this one out, I will get that, but this term will be negative. The momentum term will be switched in sign, but otherwise it will be there. This one here, as you can imagine, will be switched to a positive sign. This one here will just stay the same, that one will stay the same. So let's see what we get. We get that. We get the same number and the same options, but these two are switched round. Now, interestingly, that means that we can't complete a symmetry of this, a rotation symmetry, unless we got both positive and negative values of the p sign. What I want to do is show that this has the same group structure as that object, of those over there. And those are the traditional concepts of colour. See, red, green, blue, then an anti-symmetric one, then one that way, one that way. And in the conventional version there are 6 phases also. So that's the conventional version, and I say this is completely isomorphic to that. It's the same group structure. We have reproduced the group structure that we get for the strong interaction. We get exactly that. Color transitions in the by an exchange of the components of P between the individual, let's now call them quarks, or baryon components, or by switching the positions. So if we go back to right back here, we can either switch the P's round, or we can switch the positions of these round, and the same result will happen. But the symmetry doesn't work unless we've got both positive and negative. We can't privilege any direction, so the transition must be gauge invariant. We mustn't be able to tell which one we're in, which phase we're in, and the mediators must therefore be massless. And if we apply the group symmetry, we will know that we require 8 massless gluons. And this is what I think they would look like. There will be 6 that look like those 6, and there will be 2 out of these 3. The group structure tells us that we reduce these to 2 combinations of these 3 and not have 3 separate ones. That's because this group has a determinant 1, therefore it reduces 1. If we got such a representation, now an experiment that was done with a big input from this department was the EMC experiment at CERN, in which was shown in the late 80s that the spin of the proton or the neutron did not come from the 3-component valence quarks. It was a more complicated structure, and only a third of it came from the valence quarks. And we don't really know the full explanation for that, but possibly we're here looking at some aspect of that, because it seems to be only concerned with the valence quark for a third of the time. So maybe we ought to only have a third of the spin for a valence quark. Certainly, this structure seems to predict that you won't get the 3/2 spin of the proton coming from 3 separate halves from 3 quarks. So this does seem to be in line with the EMC experiment. The simultaneous existence of 6 phases, because it's gauge invariant, we've got to have all 6 phases at once. This is characteristic of quantum mechanical type systems. There are combination states, and then there are superposition states of six such phases. It means that identifying characteristics such as electric charges are not identifiable by their spatial positions. So we can't identify that must be an up quark, that and a down quark. That. We can only identify the total, we can't identify individual ones. And so I'm saying this is why the neutron will not have a dipole moment, because we won't be able to identify the charges, specifically as belonging to particular parts of the neutron. What I'm saying here is that U1 establishes spherical symmetry of a point charge, requires the rotation independent of the radius vector, and we did this in lecture 4. So SU3 also requires another condition. It requires the rotation to be independent of the coordinate system used. And so this here, the property we're preserving isn't the magnitude of angular momentum, it's the direction. This is an interesting aspect of this, a very interesting aspect. We've got insights into 1 or 2 fundamental physical problems. One of them is the mass gap problem. This is one of the Clay Institute's Millennium Prize problems. Baryons have non-zero mass, we know that, that's an experimental fact. And yet the mass is thought to be produced by the action of massless gluons, most of the mass at least. And although the Higgs mechanism appears to be the normal way of fermions gaining mass, say the quarks themselves have a tiny mass, and that would be by the Higgs mechanism, people think that the gluon exchange is a non-Higgs process. And they say, people talk about the Higgs mechanism being responsible for the mass in the universe. Well, it's not responsible for 98% of the mass of the proton. Now, I don't agree with that. I say that the 3-component structures clearly require the simultaneous existence of P and minus P. Otherwise, we cannot maintain the symmetry. When we got that switched by the middle two, P changed to minus P and minus P changed to P, the only way we could preserve the symmetry is having both P and minus P. If we got P and minus P, we got left-handed and right-handed simultaneously, maximally even. And if left-handed and right-handed simultaneously is the signature of the presence of mass. And so I'm saying this gluon exchange mechanism can't exist unless we've got the 2p minus p at the same time, and therefore mass, by the standard mechanism of producing mass that way, which is the Higgs mechanism. So having right and left-handed is essentially the Higgs mechanism. So I don't think they're separate issues. I don't think you've got the Higgs mechanism for the actual quark masses and then the gluon mechanism for everything else. I think they're all the same structure. That the gluon mechanism is an aspect, a realization of the Higgs mechanism for this particular structure. So it's the signature of the Higgs mechanism. So we've got a reason why we must have mass, Okay. As far as I can see, this is a perfectly adequate explanation for the existence of mass in a baryon, the plus and minus p bit. The symmetry must be maintained, even though it's done by massless gluons. And in my opinion, I have answered the requirements that they've given for this mechanism.
So you're waiting for the prize?
I am, but I can't propose myself. One of you will have to propose me. Seriously, I cannot propose myself. You can't. Somebody else has to propose you. But as far as I can see, I've answered the criteria in a way that they didn't expect, but so what? The second issue, apart from the mass, is the mechanism that's going on. So we're exchanging P's and so on between these quarks. And here, what is the actual nature of the force between strong charges? It has to have a Coulomb component. We've talked about that last time. They must all have a Coulomb component. But there is something else that makes the strong force different from the electric force. The electric force is only a Coulomb component. This is something else as well. So what is it? Well, we know there's a Coulomb component, we call it the one-gluon exchange, but there's another component, and everyone has always thought that it must be a force proportional to the distance. This deals with the strange properties of quark confinement, infrared slavery, asymptotic freedom, and so it's a linear potential has long been hypothesized. Calculations have used it. Now, if we have a non-local structure like this, exchanging P, then because it's non-local, it's got nothing to do with the separation of the quarks whatsoever. It's completely independent of that. So the force, the rate of change of momentum, definition of force, is independent of the distance of separation. That's what we call a constant force. We've got a perfectly good reason for having a linear potential from the structure alone. We now talk about vacuum. We've talked about this being vacuum, sort of like taking the fermion out and leaving with minus. And this is what is non-local to the fermion. The thing inside the bracket is what is local. Now, because we've used these operators, these suggest we can actually, these represent what we've talked about as vacuum space. Can we actually partition the vacuum into discrete components? We've got continuous vacuum, but we want to partition it into discrete components using a structure of this kind. And in fact, we can do exactly that. This object is a nilpotent, squares to 0. This object, with k multiplied by it in front, is an idempotent. It squares to itself. And what happens is if we multiply our nilpotent by an infinite number of these, or any number you want, each of these, if I do 2 of these, it's the same as doing 1, because these are idempotents. So I can do that forever. And if I multiply this by these, and I do the multiplication out, I quickly find that it just reduces to this multiplied by a scalar which can be removed by normalization. So in other words, these do not affect the structure of this. Post multiplication by these doesn't affect the structure of that. So these are the characteristics of a vacuum operator. You keep operating on vacuum and you get the same state. So that is a vacuum operator, but I can do it infinite times, of course, as I could if it was a vacuum operator. I can do the same with I and J. But if we look at this again, let's look at that again. Now let me just do this bracket here. I'm going to multiply it by k in front and k behind. And what happens is that this sign changes. That becomes minus plus instead of plus minus. These don't change, but that one does. Now, so imagine I've done that. So I've got minus there, and I've got no k there, and I've now got no k there. And I do this to every alternate one. Then I will get that. So I will get minus on every alternate one for the first term. You may recognize that structure is one of our boson states, and it's a spin 1 boson. And what I'm saying is the whole thing is simply that. But it's also that. So this fermion and this vacuum boson are the same object. The fermion creates its own vacuum bosonic structure, the same as itself, without changing anything. So every alternate state becomes an antifermion, but this structure becomes a...
But why doesn't that happen anyway? I mean, that happens in Dirac,
Yeah,
Kettenbra language.
it does. This is direct. This is
That's what I
exactly Dirac Kettenbra.
Yeah.
Yeah, it does. But what's not realised is that this structure means that you can, if you use this structure, you can then get rid of the problem you have that we need supersymmetry for. So we get similar results with those, and we get the three bosonic states. So the fermion isn't only create a boson, it creates all three bosonic states in vacuum. So from an initial fermion state, we can generate three vacuum reflections via T, P and C transformations with these three antifermions with these will be the transformations. And then we get, by the combination, the spin 1 boson, spin 0, and the boson, the fermion boson. So we could write it like that. I'm only doing the lead term. So this is using the weak operator, that's using the electric operator, that's using the strong operator, and these are what we get coming out. So if we multiply by any of these vacuum operators, we create the series of antifermion fermion states, or boson and fermion states, without changing the character of the particle state. What it's saying is that the fermion in this structure is supersymmetric with itself. The boson is simply itself, it's nothing else. It is only itself. And if we can use this object as a boson to fermion operator, this is a fermion boson operator, and we could write something like that. In the next lecture, I'm going to say we can interpret this as the alternate fermion boson loops that we need to cancel the anomalies that we have, and that people think will be solved by discovering real particles that have these properties, so we don't need them. Because if you do the calculation, you will find that you can cancel it without having new particles that have these properties. These are the particles. It has the properties itself. It doesn't need any of this. So we don't need to find any supersymmetric particles. They're actually built into the structure. And these fermions and bosons have the same energy, momentum and mass, which is ideal for cancellation. You can't get better cancellation than if they're identical in those objects. So I don't think we need supersymmetric particles because we've got supersymmetry anyway. We can now identify these as vacuum operators, and these things here as the reflections, as it were, that's just a terminology I use, interfaces produced by these. It's like you've got 3 dimensions of vacuum and you reflect in those 3 dimensions, just as you would with a kaleidoscope reflecting 3 dimensions of space. So you reflect in 3 dimensions of vacuum space and you get these structures. If we quantize and partition the vacuum, then we will get this structure. I'm saying that this is an indication that the Zitterbewegung is indeed active in defining the fermionic state, and that the 4 components of the spinner actually cancel when you write it in the nilpotent mode. And this is one of the reasons why I wanted to use discrete calculus, because if we use that, it actually cancels algebraically as well. And though we often use annihilation and creation operators as black box devices instead of quantum field theory, here we know what they look like. This is the fermion, and it's got these 4 creation operators, or those 4 annihilation operators, whichever you want. And to create the complete fermion, we have all 4 states. Or you can have some creation and some annihilation. And that's why it cancels, because we create the fermion spin up and annihilate it spin down. So the cancellation is exact, but that's only fermion plus vacuum. The totality. The fermion states and the vacuum states together cancel. If you say that's annihilation, that's creation, and that's annihilation, creation and annihilation cancel. And that's creation and that's annihilation, and they cancel. So we need 4 components to do the full cancellation, and that's an interesting fact. I'm not going to detail that though. And I'm saying a special form of the generation of bosons occurs with Zeta-Bavagon, because there you're switching between the fermionic states. And to switch from one fermionic state to another, you need a boson. You annihilate the boson the fermion you've got, and you create the new fermion, and the combination creates your boson. If you look at the supersymmetric bosons, that creation of those, you can imagine those as a result of every fermion interacting weakly with its own vacuum reflection. So every weak source is, in this sense, because it's also interacting with its vacuum reflections, it's acting as a weak dipole. The other pole being the vacuum reflection. And these exist simultaneously, these two states. So we can always think that there's a dipolar aspect to the weak interaction. There's only two direct transitions we can do. We can go from a fermion real space to an anti-fermion in vacuum space. And we would require spin bosonic state, 0. And the other is between a spin up and spin down, which already exists in the free fermion. If we look at this from the mathematical point of view, the actual source of this dipolarity, where's this dipolarity coming from? It's coming from this, that the IE operator has a plus and minus value. And this is what we said in the second lecture. Imaginary terms have this sort of dipolarity built into them. You can't do plus without doing minus as well. There's a unique feature because a fermionic source has to always be created or annihilated with its vacuum partner. You can't create one and not the other. And this is what we could call a dipolar nature. Now I've said, and this is what John was asking about earlier, but the three vacuum components originate in the concept of discrete point-like charge. That has been a part of the structure from the beginning. We can actually use these to partition the continuous vacuum. Not only are these charges, but they're also something which the continuous vacuum is partitioned into. That part of the vacuum we're dealing with the weak interaction, that part dealing with the electric, that part dealing with the strong. And that's what I was talking about previously. I don't want to go into detail of that, but that's how I envisage them. The strong vacuum is really connected with things like gluon plasma, and the weak vacuum with fermion creation. And these vacua contain aspects of the charge structures which generate them. So the vector characteristic of the strong vacuum makes baryon structure possible. The pseudoscalar makes the link between particle and vacuum, and that's for the weak interaction. The electric vacuum, I'm saying that is what isospin is all about. Here we need to talk about locality and non-locality once again. Last time we said locality is inside the bracket, non-locality is outside it. These are not opposite concepts, they're just part of one process. You've got local, you've got to have non-local. If you've got inside, you've got to have outside. You can't define one without the other. It's a duality. So every interaction has a local and a non-local aspect. You can't separate the two. Even the terms are misleading. Local actually refers to the universe as much as anything. It's not local. Inside the bracket, you've still got to have all the connections with the rest of the universe. It's not really local in the sense that it's only in that position. It's really whether it boils down to whether we're using an iterative or recursive computational paradigm. Non-local, the whole lot at once, recursive. Iterative, bit by bit, local. This is not, as we mentioned before, is not a closed system. It's a system, but it's still open. Local means everything, just as much as non-local. Now what I want to do is to show how the non-local characteristics of each interaction can be interpreted locally. So we got non-local characteristics. What is the local form of that? And the local form of that will be to tell us what the exact potentials look like. And then we can find the solutions. I want to also show that there aren't any other solutions other than these three. I'll have to go past that because I've not got time for it. I think I've talked about that. I did want to mention this, that non-local operations, to any non-local operation there's a local one, to any local operation there's a non-local one. Now when we get decoherence in a quantum system, For example, let's suppose that we've got a young slits type quantum system and we cover one of the slits up. We're doing a local transition there. We're effectively sticking in local potentials. And therefore it destroys the quantum coherence, which is the non-local relation between the information from the two slits. So we're doing the reverse transition there. We're saying we do a local thing and we get something non-local come out. So it affects the non-local. So that's the reverse thing to what we're talking about. So it works both ways. Right, the first non-local operation is nilpotency itself, or Pauli exclusion, which is the same thing. So each fermion instantaneously ensures it's got a different phase and amplitude to all the others. And that's a combination state of fermions, cannot be zero. So it's a combination state, it's zero. It is non-zero, so that's non-local. Now, we mentioned at the end last time that this was resulting from a source with spherical symmetry. If you have a source with spherical symmetry, then you will get this nilpotent structure. The nilpotent structure must be preserved, which means putting a potential energy in the energy operator, a 1 over R term. So the Pauli exclusion demands 1 over R. So the non-local structure for all the interactions demands 1 over R. And if you've got 1 over R, you've got a local effect of the non-local interaction, which is Pauli exclusion. So the second time, we got the operator P. This requires, we've already talked about that, the non-local connection between the three components of that baryon structure require a linear potential to go inside the bracket. So the non-local connection requires that local connection. The final one, the superposition state created by the 4 terms in the fermion spinner, is effectively a weak interaction. That is a dipolar interaction, or a multipolar interaction, or some combination of some sort. That one will require a local change inside the bracket, which is some sort of dipole potential, or multipolar potential. There's a lot more to quantum mechanics than single fermions, but this is the beginning. The non-local characteristics require local interactions. Let's assume we'd never had a name for these things, then we would assign names to them as strong, weak, and the electric. The strong one connected with IP, the weak one connected with IKE, because that's where the dipolar thing comes from. This is where the linear potential comes from, and this one is just purely Coulombic. I'm going to have to go straight on to this now, mathematical structure. This is the Coulomb interaction. Now, what I've said is that is what you do, that was Dirac's prescription for polar coordinates. And what I said was that you cannot get a nilpotent solution, and therefore you can't maintain Pauli exclusion without putting that in, the Coulomb term. Now we're going to solve it. But that's the thing that matters. Let's solve it anyway, because I've got no time to discuss the finer details. To solve this, we need a phase structure. We need to find the phase to which this applies. And this is the standard solution. That's the standard phase. You have to guess the phase. There's no other way of solving this kind of equation. That's the phase. I apply this differential operator to this phase, and I get something which I square to 0, which is that. That's squaring it to 0. I haven't got time to go into detail. And then what we do is take each thing in term, constant term, 1 over R squared, 1 over R, and all these can be paralleled by standard techniques. Then we just put them all together and we get the answer, and that's the Coulomb solution. I haven't done the strong interaction before, so let's have a go at that. I'm sorry, I'm going to have to go quickly. This is the linear potential, that's the Coulomb potential. It doesn't matter whether it's plus or minus, it will come out anyway. So that's what we said it must look like. That's the local effect of the strong interactions, non-local characteristics. And can we solve it? So we have to find a phase for this, and we guess what it is, because we can use the same procedure but slightly adapted and guess what the new phase is.
Why do you guess that?
Because you have to. It's like solving any differential equation, you usually have to guess the answer. Now I square to 0, and I get that, and I do a similar thing, do various coefficients, get particular equations from them, put them together, and then put them back into the phase term to see what it looks like. And I get an object that looks like that, and you can manipulate that a little bit, and you get phi in that form, and this is a sort of phase which varies more, another expression for phase, varies more slowly than that. This here you can see that there are two terms that matter. One is the first term, which dominates at high energies, and you can see that that's pretty well a free fermion solution, and that dominates. The second term dominates at low energies, and we can see that that's got a confining potential, the BR.
Why is it confining?
Because it's linear. We're saying that the linear potential dominates over that. We try the weak interaction. Now here, we don't know what the form of the object looks like. It might be dipole, it might be multipole, but let's not bother. Let's just do anything that is not the Coulomb or the strong, anything. So we have something like that. This one now, we have to guess a phase for this, so we guess a phase for that. We do the same operation, and then we do the same equations of bits of coefficients, a couple of manipulations, and finally we get an equation like that. And that is, if that was a half, there we would have a harmonic oscillator, because we got linear ends, n is linear. So we get a harmonic oscillator from this, and in fact we can make it a half by realizing we can show that this has dimensions of this, and if we go to the standard distance and so on for the Z boson, or a weakly interacting boson, we can find that that is going to be a half C. I have to leave the details of that for now. I'm leaving that out as well. In fact, we can actually do that calculation using a lot of different potentials. We can do it with a sum of potentials, a polynomial. It doesn't matter what it is, as long as it's not the strong interaction one, as long as it's not the Coulomb one, we get that harmonic oscillator solution. So what I say is that there are only three solutions with spherical symmetry of point source. And they're the ones that we recognize for our three main interactions. And we got those potentials originally from the non-local characteristics of the interactions, not from the local ones. I think I will leave most of the rest, because I'll leave you to read it yourselves, because that would be too difficult to explain now, but I'm going to go to the end. I'm saying ultimately the broken symmetry between the interactions, which these structures manifest, that's why they got K in front, that's why it's got a vector in front of the strong one, emerge when the 8 base units are compacted into 5 composite generators. We modify time, space, mass, and ultimately charge in the process. And the modification of charge, which is what we're talking about today, shows the non-local vacuum side of the compactification process. And the compactification to energy, momentum, and rest mass shows the local. And we'll talk about that in a later lecture. And the different algebraic characteristics of the three components ultimately determine the local interactions that we can do. And if we follow this very carefully, we can see we've gone all the way from the non-local vacua to the actual physical effects, which are characteristics of these forces. And that's where I'll stop. Thank you. There's a little bit more about...
Just one very quick question. So you're producing the existence from 3 by 3 of 8 plus 1.
Yes.
What is the 1?
That's the singlet state, yes.
So you predict a singlet gluon.
Well, it's just the same as conventional. This group structure is exactly the same as the conventional one.
But you actually explicitly here, if we follow...
I'm not sure about that. I can't actually... I'll have to think about that. I don't know the answer immediately, whether I actually predict a real particle or not. I'd have to look at it, but I do know that the conventional theory does. That's the standard Coulomb solution.
Yeah, but there's a big step in there when you went and did an operator on a phase. I did not...
No, that's what I've discussed time and time again in quantum mechanics, and in the last lecture I said that was how we did it. You do operator on phase squared equals 0 is what I do. I don't just do Dirac equation. I have a new method, and that's what my method is.
And that comes from what in relation to your nilpotence?
That comes from the fact that the key thing is that Pauli exclusion occurs to every fermion in the universe. And that to make Pauli exclusion occur to every fermion in the universe, that's what you have to do. And that's more important than any equation,
Exactly.
more important than anything else.
Exactly, but why was that statement I forgot?
Yeah, well, that was what I did, and that's the reason.
So that hyperpoint, that contains the Coulomb quantization, that contains the spin-orbit interaction and the relativistic mass correction.
That's
It's
correct.
come out in one go.
But so does Dirac.
Yeah, so does Dirac.
But if you do Dirac, you've got to actually have two separate equations which you intersperse with each other. This is key because I can now solve things that Dirac hasn't solved.